Are we live? Are we live? Okay. Welcome, guys. Sorry for the problems that we are encountering currently with the display, it seems. So, welcome to the last lecture for the binary exploitation. So, as mentioned in the site, the challenges will be due by Monday, uh, April 29th, and after that, you would be free to um, complete the challenges, but with 50 percentage until the next Monday, next Sunday, if I'm correct. Let me open the site. Um, Kindly bear if the display doesn't show properly. Uh, so, as shown here, the module is due in 4 days. Um, and afterwards you can submit the uh, thing until the Sunday, but it will be accounted as a 50 percentage of the submission. And we saw we started with the shell coding in this chapter. We saw that uh, it's a type of injection in which it provides the better flexibility of spawning. It's about spawning a shell process, and then once you get the control by spawning a new shell process, you would be able to get control of the complete systems, and would help to compromise the system. And the cell the this primarily happens because most of the architecture the Intel and other ones are one human architecture, and that provides an opportunity to inject the code into the uh, buffer, or inject into the common memory, uh, in which the computer exports for the data, and then the attacker can inject a specific code, mm, and which can spawn a shell, and from that shell you would be able to um, gain a complete control over the resources by providing by um, uh, controlling the flow of the control data to whichever way we want. So that's the gist of the shell code, and we saw with an example of with an example here of how, yeah, then data is being interpreted for code, and then it's get run as a code. And we saw an sample shell code that's that spans their shell, and we saw uh, the code can be given in any type of form. So, for example, here you are provided with the ASCII values, and like you might have already attempted the challenges for the three shell type. It need not need to span the shell code, so this is one of the non-shell type of shell codes, where you open a specific file, and in this example we are opening the flag itself. The main advantage of here is that we are injecting the shell code on the compromised application. So the application would be running with the privilege of the executable privilege. And if the shell code spawns from the applications, it will also have the privilege, escalated privilege of the application, and we will have the complete control over the resources. For example, the application would be executable as a root, and the shell code, the shell that spawn out of the application from being injected into the code, will also have the escalated privilege, and we would be able to complete control over the shells. Uh, and we saw an example of how to compile the shell code, and then we will copy only the raw byte of the shell code, and we use it to pipeline into the buffer. That's what we saw. And for today's class, we would see in the application how we can uh, launch the shell code using the return address. So the sample shell application and the first three levels of application that we saw, it didn't actually had the actual shell. It didn't spawn a shell, but it actually made a system call and then run a system call. Uh, uh, but it demonstrated how a system call can be made from a buffer. Since we pipeline that code into the buffer. Uh, in today's module is about the application where you will get into the gist of how to specifically launch by overwriting the buffer, get to know about where the return address would be, and then make the specific return address or able to write the code after the buffer overflow, uh, and launch the specific shell code, intended shell code. So that's the we are getting into the crux of the actual binary exploitation of launching the shell code by doing the binary exploitation. Um, and and in the last class we saw in the binary errors as the, so we will quickly go over the uh, the slides again. So we introduced about the shell code, which is nothing but spawning a shell or calling a system call from the memory. That's because of, since the basic architecture of having the both, interpreting both the code and the data in the common memory, and by manipulating the data, we are able to make a system call by user defined attacker code, attacker data. We are able to make a system call and then achieve the shell code. That's what the introduction went about. And we introduced about the memo, the the one of the basic vulnerability that happens across all the systems. That's the buffer overflow. And the reason the buffer overflow usually happens, uh, for not for every languages. Most of the languages that get affected is the C and C++. That's because C provides complete flexibility to it provides a high level languages, um, uh, but at the same time it is left to the developer to make precautionary steps of not to go out of bounds of the array, or other criteria that's left with the developer itself. So it gives the complete. It's one of the advantages is portable to multiple architecture, and it's close enough to control the resources of the assembly with no inherent uh, mm, uh, check for the vulnerabilities, like we saw for overbound in array or writing the bum memory. So we saw that it's already been discussed, like you saw here in the slide. Already been discussed about the problem with if some other application, without having a separate address space, and yeah, another application having the uh, uh, getting access to overwrite the memory of different applications. But the C doesn't provide inherent. We have the we have specific library functions to make to to check for any overwriting of the memory or not to go out of bound of the memory. But uh, other than that, it's very flexible, and it's upon the developer to take due care such that the memory is not overwritten. And in spite of the this drawback from the C has been widely used. C is still the popular languages. The reason is that it's the same advantage of flexibility and the fastness of the code. So in the compiled languages, you may not be able to achieve uh, the fastness of the code, and it's being used in all for developing code for all the embedded uh, processor, which is not powerful enough to incorporate the high level programming languages. Uh, so the C provides the C is still the popular languages because of its portability and being used in many of the embedded devices. That's what we look, we went over the basic problem of mixing of control information and the data information, in which whenever a function is called, you have to do a function prologue of saving the return address, in which the return address specifies the control information and then the other local variables which is created in the stack. And after the stack has been completed, it will get to know about the return address, the control information of the return address from the stack itself. So when it's been overwritten with malicious data or accidental data, you get the problem. And this is the same problem is the reason for the first documented uh, attack that we know in 1988, the Morris worm that was launched in the MIT lab. It basically exploited the buffer overflow and able to spread across the different architectures. And the third problem we saw with the kind of the languages in C is that it also mixes the meta data and data. So, for example, the string is interpreted as a completion of the string using the null bytes. And what will happen if the null byte is inserted in between, or if something is accidentally written with the null bytes, then it will be interpreted incorrectly, and that would be the case for its usage in functions such as string copy and other kind of library function. So that's another problem. And also with the as we already mentioned, that it's left to the users to clean up or initialize the data. And then we saw with an example of how to smash the data and make it overflow. So once you s- you smash the buffer and make it to overflow, you get to the uh, other part of the uh, return address, and one you can able to correct the return address, which will point to a different location and then cause a segmentation fault. Or else you can specifically direct the return address to the specific location of the program, for example the shell code, and make it run the malicious code that we will be going to see for today. So that's the opportunity that it provides without for the that's the inherent uh, trouble with not being able to checking with the memory overflow, and it gives we can be able to override the return pointer, and then it can we can direct the control flow into the specific thing. It basically happens because there is no inherent check. For example, in this yes printf, uh, the output size is of 16. So when the input is go out of bound, then it overrides the output, and if the output directs to the specific user defined function bin function that will read the flag, it will execute that function and then we will read the flag. So that's basically the memory corruption. And we also saw the causes of the corruption, uh, as um, uh, the basic buffer overflow, and then we also saw that it can also happen uh, of because of the mixing of the signed and unsigned. So for example, in the program, the integer variable, that the assignment of the variables would be signed integer, but the the data type that is used in the library function would be the unsigned type. And we know that the unsigned and unsigned would be uh, uh, the C languages uses to complement integer, and the comparative will specifically use, for example, in this kind of two comparisons, the one would be checking with the signed one and the other would be unsigned one, and this would cause the incorrect mixing up. The same thing can hold for the integer overflows and off by one error, in the sense, like for example the string, probably we may not be able to, the developer would forget to uh, account for the null character at the end of the string, or else similar to the integer overflow, uh, the end of the integer may not be accounted for, and it will overflow to, for example, incrementing the value to the next one would overflow to the minus one. And that's what we saw up to the previous one. And I remember we haven't seen about the canary, and what are the different ways that we can um, able to uh, control this, avoid the stack overflow. One of the uh, method is the usage of canary. So we know that canary is a type of bird. The miners would use it. They would carry it in the miners, and if any toxic gas is emitted, it's very sensitive to the toxic gases, and it can die immediately. And if they find that canary uh, is being affected uh, by something, I think, then means that it's because of the toxic gas, and immediately they will evacuate. The similar kind of checking is implemented in the software. So here we are trying to implement in the software by before and after the making a function call in the function epilogue and function prologue and the epilogue. So in the prologue, we will be saving the return address, and then we will create a new stack pointer, and we will save the current stack base uh, uh, stack pointer and the base pointer into the stack, and then call into the new stack with the return address also. We will push it into the stack, and the new base pointer and stack pointer will be created with the return address being pushed into the stack. And in that prologue itself, we will create a random value, and then once the function get finishes in the epilogue, we will be checking with the random number, and if it is correct, then we will be sure that it has not been overwritten, and so we will continue with that. So if it is not equal, then that means that there has overflow has occurred, or malicious overwritten has been occurred, and so it will stop, it will make a exception, and will discontinue. So it's one of the important thing that's being currently also being used. It's proposed at 1998. It's been currently being used. It's very effective in preventing the overflow image even at present. So by default, I think depending upon the architecture, this will be implemented. So for our challenges, the challenger would specifically do not compile with the stack analysis, or it will instruct to not to use the stack analysis for the compiling. But the default is that it would be the stack analysis that would be implemented. If you have to disable it for example, for the development purposes, then you will have to use F no stack protector compiler option. The other one is the uh, random stack layout. So here the OS always makes the predictable layout, and that makes it possible for the attacker to uh, predict or estimate where the code would be, and do malicious overwriting of specific part of the uh, code in the memory. So, what would happen if it's being randomized? So, that's the concept in the address space layout randomization. So, it's been proposed by the PAX team, which the same has implemented DEP. If you remember DEP, it's the it's the it's the prevention mechanism that we discussed in the shell code as data execution prevention, in which we will get to know about the shell code happens uh, because uh, the code being injected into the area which is intended for data, and so the OS specifically proactively uh, uh, protects that restricts the area in which is been dedicated for data. So currently, all OSs will not allow any code to be executed from the stack. And if you have to, if you have to change it, we have to use mprotect to change uh, the permissions to read or write or execute. That's the default thing, and the the same thing was proposed by this team, the DAP, and here it will randomize the different portions of the code, and hence you would be able to prevent the malicious intent overrating by the malicious attacker. If you have to avoid this, then you have to use the ASLR equal to false. Yeah, so that's why we started so late. So there is a query that to zoom out, something was problem with my display. That's why we started so late. I could not able to control the display. So please bear with me. Yes, I can try with. Okay, I think I made a. Okay, I think it's getting good. I think so. We use the ASLR to randomize the layout and the area of the memory, such that it prevents the attacker from guessing or predicting the exact location, and prevents them from uh, modifying the code. So that's the basic idea behind the idea behind the SLR. Uh, and for today, uh, we are going to do the actual thing of exploitation after we saw the actual different kind of memory attacks and how we can be exploit. We also the next slide also discuss about how in spite of all this we can be able to uh, reveal the core in spite of all this protection and the cost of disclosure. For today's thing, we will go over to the main thing of the program exploitation with all the things that we learned. That means we learned about the shell coding, we learned about the program exploitation, but in the shell coding slides that we saw at the beginning, we show that what the shell code is about, and we showed them a simple shell code of for making a system call, and then we pipeline into the buffer such that the code will get into the buffer and then it get executed into the buffer. But here we will see, for example, uh, how can we get to know what's the return address is actually, and then make modify the return address or specifically load the shell code into a specific location and make it run specifically. So we will overflow the buffer. Uh, we have lot of other kind of thing. It's about making getting use of the things that we learned in the shell code and the buffer overflow, and then do a program specific exploitation by using either overwriting the return addresses or carefully crafting the payload by storing it in a specific location, and then make that return address to be stored in a specific location such that the attacker can achieve the intended control flow, or getting complete control over the resources. Um, so this gives so before going into that, so how do we achieve control usually? It's about first to get to know about what are the things that we can able to get in control. So for example, like we saw in the previous one, we will come to know, is there a possibility of overflow. We will see whether there is a canary check is involved, or the ASLR address space layout randomization is involved, or if there is a address space randomization, how we can be able to predict, at least even with the ASLR implementation, we can be able to um, uh, guess and then predict the address using the because of the page memory architecture and the last 4 bytes nimble can be easily guessed by repeated trying of the thing. So by by recognizing different thing that we able to achieve, and even with a small foothold, and then repeating the process of finding out how much we can gain control, you can increase the influence and make it into a complete compromise at the end. That's what revealed by the Phineas Fisher. If you can get to know more about the team who able to hack major things that you can see in the information in the web, in the online. That's the strategy they also develop, and this is the strategy good that we need also to adapt. We have to first look at the program and understand it, and we have to find if there could be any tiny opportunities that we can exploit, and if there is a uh, if there is something, then we have to exploit it and then see how we can increase that initial corruption to open up for further uh, opportunities to make more influence, and then finally get into the total compromise of the system. That would be the strategy to be to use uh, for uh, compromising and getting hold of a system as an ethical hacker. So, as mentioned here, it's more of an art rather than a science. We have to learn by practice and from experience. And in for the challenges, we have four um, exploitation related with program exploitation. For example, today we will see simple hijacking of shell code that we saw. So, as I mentioned in the initial, we saw the shell code explanation that pertains to what the shell code is about and how, and we saw the demonstrator in the first three challenges of how we inject the shell code into the uh, buffer, and then but the by the by since we compile the buffer such that it will execute the code like uh, uh, code execute the execute stack option, it's able to execute here, but we will see here like how we can carefully extract such that as it exceeds the buffer, we can able to uh, change the return address such that the control flows to the specific shellcode that we store, or after the buffer overflow to the return address, we can write the shellcode. We can place the shellcode in that area and make it execute. So, for example, this is the shellcode that we saw in the when we introduced the shellcode itself, which demonstrated that just by changing the arguments in which the arguments expect function in the second argument, we change it to name, we make it to uh, corrupt and cause a segmentation fault. And even if we have to change, even if we make it the correct arguments also, it still has the vulnerability because of the gets function that we set, in which it doesn't uh, examine the bounds of the input, and the if the user inputs more than the buffer size, he would be able to uh, overwrite or overflow with the buffer, and the return address would get corrupted and will cause the segmentation fault. Uh, we can craft this into the specific location and then write exactly uh, the shell code uh, that we wanted to achieve. So, for example, we saw in the shell code in the beginning of how to read the flag, we can use this same shell code, and then we can we can place it in the specific return address and make it run from the specific site. So if I can run it. Yeah. So here we saw the write and execute shell code in which it makes a system call, and we pass the shell code into the buffer, and it basically, because the we execute with no the- we allow it to execute with the option of execute stack. it runs the stack and read the flag. Here we will show with the same example of the placing the code into a specific return address, and then we manipulate the return address such that it we use the same strategy of going into the specific address, and then we can read the flag. So let's go and start the. We will do some demonstration using the same thing in which we won't pass it on the as a we won't give as an input to the buffer, but we will modify the return address such that the shell code will get executed because of the specific manipulation of the return address after the overflow of the shell buffer. So let me open. So yeah, we can use the same code here. And then we will make it such that instead of passing the shell code, we can modify the return address, and then we will make it to go to the specific return address, and then we can run it. So if we can create a so for example overflow. Okay. So the way to compile is so does anyone knows what this stands for? So if I have to compile and then if I have to make it run, then by default it will implement the stack canary, the OS, and it won't allow it to uh, do the exploitation. So, for example, yeah, if I so the we have to compile using this option if you have to make it to do buffer overflow. Otherwise, it will implement the default stack canary, and the stack canary will check after the uh, um, function call. It will check whether it has been overwritten, and it will stop it, and the segmentation fault will not occur. That means we won't be able to continue with the program and modify the return address if you don't disable the stack protector. So this is for disabling the stack canary, and this is to allow for the data part, which is the stack part, to execute the code. So that gives the execution privilege to the code part also. So we have to compile it using F no stack protector, which will prevent which will disable the stack canaries, and we have to enable stack execution. If I am correct, it's exec stack, that's the option. So, and then you can just make the output. Yeah, so we have compiled and it shows the errors which is inherent with the GCC. So once we compile it, we can run the code and then see for anything that has the problem. So for example, to run the code, we'll just do hello, and to disable it, we have to do the we have to run with so of course, for example, for simple hello, it will print hello. But if we increase more than 1,000 thing that mentions the thing that mentioned in the code, uh, so if it goes beyond 1024, it has to create the segmentation fault. I think this could be because of the inherent capability of the ASLR. So I'll set the architecture to x64, and then I will disable x86 64, and the R option disable the ASLR. Um, and then if you run hello, so the segmentation fault occurs. And if we get to know, oh, from the GDB, so I have used the source of the JAF in my GDB init source file, and so it can automatically show at the time of, so it caused the segmentation fault. At the time of segmentation fault, it will automatically show what is the stack, uh, the backtrace of the stack, and the PC address, program counter. So it shows that the thing happened. So that the segmentation fault is the exception signal that happened, and it's belong to 552E1, and the Jeff is able to automatically show here the return. So it stopped exactly at the return. Once it left um, the 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 stack, after the stack in the return address, this was the fault, that it didn't represent the exact value, and the RSP referred to the thing that I typed here. So if I have typed AAA, something like that, so it would show exactly the AAA, and you can see the contents of whatever that I have typed here using the JAF. Um, if I if I if we have to we have to then go to the specific location, and then instead of that segmentation fault on the return, if we have to use the specific address or even write the exact code on that specific location, we can do that, and that would be the idea behind the program exploitation. Go to the specific part and then where we can place the address, and then we will get to know what the return address here. In that return address, by modifying the return address, you can you can direct the flow into the specific code, which is a shell code that's the created by the malicious attacker, and then achieve the intended behavior that the attacker wants to achieve. That we can do it using using the PAN GDB. So the time is, yeah. So we will probably we can quickly go over how we can do it. Um, uh, it's simple that we can use the you can use the pawn tool, specifically pawn debug tool, and you can so if I so there's a GDB tool. Similar to the pawn dot process, we can start with the GDB itself that provides the flexibility of immediately seeing after we supply some input into the GDB that like we see in a quickly moment. So if we can, so we can do, for example, hello. And we need to disable ASLR also. Okay. So as you can see here, once you run it, it will automatically open the debug here, and uh, it will have the parallel. So it will attach a debug, and then once we make the input, as we saw in the previously, it will automatically stop once it been it's been stopped by the segmentation fault. So if we can run it here, I can supply for you can send it through the thing using the write, but actually our intention here is to is to know where the offset is. So we have the in the previous one, like it shows the previous one of the, yeah, at which, so we created from here. So previously we had this intention here, and we had the return address being, currently the return address being here. After the 00, the return address would be there. How to know from the start of the return address? Suppose if at the start the RSP is here, and we want to know how much the offset is there, and after the offset you have to place the return address, which is here. If you want to know that, we can do that with a Python debug tool, with the pawn cycle tool, in which you will input a specific uh, pattern, and then once the return segmentation fault is created, we will search for the specific pattern, and then we can calculate the offset, and using that offset you can place the code there exactly at the position, and then may achieve the intention. So for example, we have to, so you will enter, for example, we saw that it's 1024 bytes long for the name, so we can put simply 1000, and then as this is a 64-bit architecture, we can put 8. That means it will write in sequence of 8 bytes. uh, this will this will write, think I will add a bit of newer here and then close it. This is what this will get written, and you can see here this should have caused the, so it's stopped. Just want to make sure the next class doesn't comes. So you can achieve here and then stop it. I think I have to restart the process again. Okay. And if I intend to write, it will create a, sorry. I'm sorry. It should be, so this is the byte that will be sent, and we have to send it to process. And I'm sorry, I used this. So this will go to the process, and we should be having the exception being segmentation fault being created. And you can see here it has created the segmentation fault, and the same thing that we saw in the beginning has also been shown here with the thing. But current now we have to calculate what is the return address here. So we can calculate the return address that we the position of the return address, how much it is offset, can be calculated in the point tool itself. Okay, so if we find out the specific location for that address, so we look for the RSP that contains the value. Currently, after the overflow, this contains the value. So this is the value, and this is the address of pointed to by the RSP. So using this value, which corresponds to using this value, I can check cyclic find, and then we use the 8 bytes, the length. It will show the offset because we just now found out that the signal RSP in which the return created the segmentation fault has the address of this, and the value is here, and we are looking for that specific address, and that's that this will show. So the offset is it's 1032 bytes long. So we can use this offset to create the smashing, and then after the after the smashing, so we are get to know the offset exactly. That's what the intention of the attacker is. So once we know the offset, we can place the intended return address or directly the code. So the next thing would be you can in the next time you can start the process again and then write the same thing. So you can start the process again like this, and then now you can write the specific with that we will close quickly with that uh, you can write p dot write. Since we know that it's 32 bytes long, we can smash it with a specific byte a star 1032. That's the intended plus. um, it's a little endian, so the address of the last return address value that we found out, that was we just copied. That is this is the one of the address plus 8 byte. Uh, the next one, since it's a 8 byte architecture, plus this is where we have to enter the code. So if I have the shell code specifically, you can convert it into the ASCII, and it will have, for example, F0, F1. So you can place all your shell code here and then end up with a new line character. Shell code or the return address of the shell code or a specific return address here, such that it can point out to the specific code, and then the byte value, new line character. This will specifically place at the intended location. So we have correctly find out with the program what is the offset is and how we can place the return address here, and with that placement it will next time it will write it, and it will correctly overflow with the exact number of bytes, and then it will transfer to the either correct code or intended return address. So that's the thing that we are trying to achieve with the program exploitation. And I know that we started very late. uh, I will try if I can make an office hour extra to cover. I will let you know if it is possible. But otherwise, the due is on Monday, and after Monday, it would be 50%, and you can submit for any different module. Let me know if you have questions. I have an office hour tomorrow. We will discuss it. Thank you.